All right, so this is chapter 5's review activity, and it's all about different kinds of reactions. So, what you should do is you should be able to look at any given reaction and be able to classify it. Is it synthesis? Is it decomposition? Is it condensation? And so, the ability to be able to do that, you have to know what kind of things to look for. So, what you should do is create an example reaction for everything that we learned in class. And then, if you know the example, you can apply it to whatever situation you find on the exam. So, you should go in and try to make these from your notes, from your textbook, and then just check my answers. So, if we start with synthesis, we're going to use A and B as reactants. So, if A is a reactant and B is a reactant, what am I going to make? Well, if two things join together, then it would make AB. So, anytime you have two reactants going to one product, it's an example of synthesis. And now, what we're not going to do in all of our examples is you'll see sometimes we'll do a single-sided arrow like this, and sometimes we'll do a reversible arrow like this. So this type of arrow tells you if the reaction is reversible or not. So if you have a double-sided arrow, that means it can go forward and reverse. So this is reversible. But if you have a single-sided arrow, this is irreversible. So you can only go in the forward direction, whereas a reversible, you can go in the forward direction and the reverse direction. All right, decomposition, use A, B as a reactant. So here we have one reactant, and then we're going to decompose it into A plus B. So we got two products. And it might be one reactant and three products, but you're starting with one thing and you're breaking it down. All right, exchange. So exchange can either be a single exchange or a double exchange. And so if we were going to do single, so I would start with AB as one of my reactants. Okay, but that's not going to be enough, right? Because if I just do something with it, then it would be a decomposition and I would break it up, but I don't want to do that. So I'm going to add something else. I'm going to add C to it. So what's going to happen is I'm going to have an exchange. I'm going to exchange out where I had B, I'm going to exchange it for C. So those two are the ones that are going to exchange. So I'm going to get AC plus B. So this is a single exchange because I only did one exchange here and here. If on the other hand, I did AB plus CD and I exchange out either my non-metals or my metals, whichever one, I got to pick one, right? Here, I'm going to have an exchange and make two new compounds. In the above, I only made one new compound. The other one is an element. And so what I'm going to do is make two new compounds in a double exchange. So what I'm going to have is A, and not B, but D. And then I'm going to have C, B. So all I did was exchange, but we're exchanging between two compounds to make two new compounds. Okay, combustion. And it says to use CXHY. So for some number, this is just a hydrocarbon. All we're saying is that we have a hydrocarbon and we're going to combust it. So you have to know what the other reactants are in a combustion reaction. Combustion reactions always have oxygen as a reactant. And just kind of think about it. You have to have oxygen for a fire to burn. So if it's combustion, you're going to need oxygen. And then in complete combustion, so this is technically complete combustion, you're only going to make two products. Your only two products are carbon dioxide and water. And that's it. So there could be incomplete combustion, but you would also have carbon monoxide as a product. All right, condensation. We're supposed to use R1-OH as a reactant. So I'm going to start with that, R1-OH, but that's not the only reactant. I should have something else there as well. And so I'm going to have another molecule that has a hydroxyl, just like my first molecule, except this is going to have a different rest of the molecule. So we're going to call it R2. So the whole point is we're going to start with 2 small molecules, right? And then what I'm going to do is we're going to make one big molecule plus water. So where does the water come from? Well, what is water? Water is HOH. So what I'm going to do is, let's do it in blue. Water's blue, right? So I'm going to take a hydrogen from one, and I'm going to take a hydroxyl from the other, so that I end up having all of the elements that I need to make water, HOH. And then all I have to do is look at the rest. What's left? I have an R1, then it's bonded to an oxygen. So let me write that. I have an R1, it's bonded to an oxygen. But if the oxygen doesn't have a hydrogen there, it's lacking a bond. And if I look over at R2, my R2 is missing a bond, right? It's normally bonded to an oxygen, but it can't be anymore. So what's going to happen is we're going to get a new bond that forms between R2 and the oxygen. So I have my R1, I have my oxygen. Now I just have to add my R2. And that's it. And then if we look at hydrolysis, in hydrolysis, we're kind of doing the reverse, right? Here's our reactant, R1O, R2. That's the only reactant that's given to us. But is that the only reactant in the reaction? No. I'm also going to need water, because this is hydrolysis or hydrolysis. Hydro meaning water and lysis meaning break. So we're going to break water and we're going to break our other reactants. So I don't like to write water that way. I like to write water this way so that we can kind of track what's going on. And these are actually, a lot of times, these are reversible reactions. So we tend to draw them with a double-sided arrow. Okay, so what am I going to make? Well, you got to kind of think about, okay, I'm going to break water. Well, how am I going to break water? I have to break either the bond on either side of the oxygen. I can't break a water molecule perfectly in half. So I'm going to have to break one of those 2 bonds. It does not matter which one you break. Just break one of them. All right. The same thing is going to happen with our other molecule that has an oxygen. You're always going to look for an oxygen that has a carbon on either side of it. And so that's exactly what R's are. They're things with carbon inside of them. So break your molecule that has, if you have something that has a C, it's bonded to an oxygen, bonded to a carbon, right? And it's bonded to 4 other things. We're just not showing it. This is the same thing as ROR, which is an ester, right? So, and you could also have ethers that fit this definition. But it's typically either an ester or an ether. And I'll show you an ether looks very much like an ester, except it's R carbonyl OR. But you still have, this has carbon, this has carbon. So if you look at your oxygen, on one side you have a carbon, on the other side you have a carbon. So you still have that, that carbon, oxygen, carbon pattern. So once you find your carbon, oxygen, carbon, let's kind of erase some of this. Okay, what you're going to do is you're going to cleave on either side of the oxygen. Does not matter, just pick one and break it. So that's where my 2 break points are. So what's going to happen is I'm going to make 2 new molecules. So I'm going to start with one big molecule and water. And what I'm going to end up with are 2 small molecules. And we could add a little thing here. Each will have a hydroxyl, just like in a condensation reaction. So I'm starting with two small molecules in my condensation reaction, and I notice that each of them has a hydroxyl. So each with a hydroxyl, right? Okay, so now I got to predict my products. So I'm basically going to do the same sort of thing. I'm going to say, all right, I need to make some new bonds. I broke some bonds, so I need to make some bonds. So if I come over here and I see R1, R1's right here, this R1 doesn't have an oxygen next to it. It's so sad it doesn't have an oxygen. So you're going to come over to the water and you're going to give R1 an oxygen and a hydrogen. But just remember that R1 does not make a bond to hydrogen and then hydrogen bonds to oxygen. That doesn't work. Hydrogen can only make one bond. So your R group is going to bond to the oxygen. So I'm going to say that's R1 dash OH. So there's my hydroxyl. So I have one small molecule with a hydroxyl. So what's left? Well, if I look at what's left, I have an R2 bonded to an oxygen. So now what's going to happen here is this oxygen is going to pick up the hydrogen that's left over from the water. And so what I end up with here, so this is the blue stuff, right? Oops. This is all the blue stuff. And then we're going to make R2, and I'm just reading it this way, right? I'm reading R2, and then it's bonded to an oxygen, and then the oxygen is going to come over and, ooh, picked up the wrong arrow. It's going to pick up this hydrogen, so that each of our new molecules now has an R group and a hydroxyl. So we have a hydroxyl here and a hydroxyl here. So that's the difference between the different kinds of reactions that can happen. There are some reactions that are opposites of one another. And so if you kind of look up at the top and look and see which ones kind of look like, well, it's the same reaction, we're just writing it in the reverse way. So that is our synthesis and decomposition. Those are opposites. And then you should have looked above and seen that also condensation and hydrolysis are also opposites of one another. So what you could say is that if you did a condensation reaction in this direction, you're doing condensation. But if you do it in the opposite direction, you're actually doing hydrolysis because you're breaking the water. It's the same thing, you're just doing it in a different way. So our condensation reactions, could you think of another name? If you look at that condensation reaction, what are we doing? We're taking two things. So I'm taking two things, and I'm making one big molecule. Yes, I also make water. So it's not really just two things going to one thing, but I am taking two smaller molecules and making one big molecule, and kind of my byproduct is water. So a lot of times we can call condensation reactions a type of synthesis reaction. So hydrolysis, if hydrolysis is the opposite, then hydrolysis reactions could be called decomposition. And I'll show you that. Because I'm starting with one big molecule. Here's my one big molecule, and I'm breaking it down into two smaller molecules. And so this is just to kind of look for patterns in the different reactions. So oxidation reduction reactions are sometimes called, it's just the shorthand, redox reactions, right? They are so important. And it's really important that we can look at a chemical reaction and track electrons, hydrogens, and oxygens. It's going to be one of those three to determine if oxidation is happening or if reduction is happening. And this is not going to be given to you on the exam. So you need to know this. So the way that I remember this is the little mnemonic oil rig. So this stands for oxidation. So oxidation is loss of electrons. And because it starts with an O, it's going to gain oxygen and lose hydrogen. So then if you remember oxidation, reduction is just the opposite. Reduction is gain of electrons, gain not of oxygen, but of hydrogen, and then loss, or you lose oxygen. So you just have to remember that they're opposites of one another. And what I would do is, as soon as I got my exam, I would write that on the top of my exam. All right, so now we have to talk about what's going to happen. Well, if we have something, for example, that starts as an aldehyde, and I know this is an aldehyde because I have a carbonyl. So here's my carbonyl right here. It's a carbon double bonded to an oxygen. It's bound to an R group on one side and a hydrogen on the other. If it were bonded to two R groups, if this hydrogen were an R, then it would be a ketone. But in this case, we have an aldehyde. So if we're going to undergo oxidation, remember we said you could gain oxygen, you could lose hydrogen. And that tells us that we are undergoing oxidation. So what could happen? Well, I'm going to keep my R group. My R group's not going to change. And so I need to look at what's going to happen to my carbon. In my initial substance, right, my carbon is attached to one oxygen. But if I now attach it to two oxygens, so see how I picked up this oxygen? This carbon double bonded to the oxygen in the carbonyl has not changed. What I've done is, in place of having a hydrogen here, I now have a hydroxyl. So I have gained oxygen. Okay, so that gain of oxygen allows me to make something that has a carbonyl, and that carbonyl carbon is bonded to a hydroxyl. And so we call that a carboxylic acid. And that's always where we are either gaining oxygen or losing hydrogen, and that is oxidation. That's how we know oxidation has happened. So did I lose hydrogen? No. But I did gain oxygen in this example. So I know oxidation occurred because I gained an oxygen. Now, if I take that same aldehyde and instead of oxidizing it, I reduce it. Reduction in this case is now a gain, not of oxygen, but a gain of hydrogen. Maybe a loss of oxygen. And so if I take an aldehyde and I reduce it, that aldehyde is now, I'm still going to keep my R group, but a reduction means that we're going to lose the double bond between the carbon and the oxygen, and we're going to end up with a hydroxyl attached to the carbon. Now, this carbon's incomplete. It doesn't have 4 bonds. So in order to complete its octet, it's going to pick up another hydrogen. So my question to you is, did it lose oxygen or did it gain hydrogen when it was reduced from an aldehyde to, this would be an alcohol, because we have our hydroxyl right here, and that tells us we have an alcohol. So what's happening here, if I count my hydrogens, right, I have 1 hydrogen here, but then when I look at my molecule, I have 1, 2, 3. So here I have gained hydrogen. That's what's actually happening in this reaction. And so that's how I know it was a reduction reaction, right? So this is where we add like H2. Okay. The next set of reactions are all about alkenes. Alkenes are reactive because they have a double bond. And because that double bond can be broken, where we can take the molecule from having a double bond between the 2 carbons to a single bond, when we do that, if I were to simply, get my eraser out, and erase one of these bonds, right? Is either carbon happy? No. Each carbon only has 3 bonds and it wants 4 to complete its octet. So if this happens where that double bond is broken, each carbon that participated in the double bond wants to pick up something else. So the first carbon might pick up the X and the second carbon might pick up the Y, or vice versa. It kind of depends on which reaction you're doing. But now we're going to form new single bonds between each of the carbons that participated in the carbon-carbon double bond and the different parts of the small molecule, right? Now, this doesn't happen readily. A lot of times you have to have a catalyst that's needed. So usually it's a heavy metal like platinum or nickel or palladium, right? Those are all examples. And so if we had a catalyst, we would write that symbol either above or below the arrow. So in this case, because there's already something above the arrow, what I might do, and I'll erase this stuff, what I would do is I would write like that was a platinum catalyst and put it right under. Okay, so there are a couple of different kinds of addition reactions that you can have. The first one is called a hydration. Like if you ever said, oh my gosh, I'm so dehydrated. What did you not have enough of? I didn't have enough water. So a hydration is adding water to something, right? If somebody tells you, you need to hydrate, you need to drink more water. And so we can use a hydration reaction to show this addition. So hydrations are just a type of addition reaction. So what happens is you break the water, right? Just like we did before. And we also break one of the bonds in the carbon-carbon double bond. So now one of the carbons is going to pick up a hydrogen. One of the carbons is going to pick up a hydroxyl. So in order for this to happen, you have to have it in very, very acidic conditions. So the kind of catalyst that you need is usually an acid, or sometimes they just write it just as H+, and that just indicates that you have an acid in there. And that just means you have a low pH, right? So where do we write the symbol? Just like here where we said, here's the acid, you write it above or below the arrow. Okay. So does it matter which carbon got the hydrogen and which carbon got the hydroxyl? It does matter. And I'll show you some examples in just a few minutes. But really, if you look at each of the carbons, in order to determine who's going to get the hydrogen, you have to look at the carbon that already has more hydrogens directly attached to that carbon. So if this were a hydrogen and this were a hydrogen and this were a CH3, well, CH3, that's crazy. CH2, CH2, CH3, and this were a hydrogen. I would look and I would say, okay, that carbon number 1 and this is carbon number 2. So carbon number 1, excuse me, has 2 hydrogens directly attached to it. Carbon number 2 only has 1 hydrogen directly attached to it. The other thing is a carbon, so it doesn't count. So here, I would have to have that first carbon pick up the extra hydrogen, because this is a hydrogen, this is a hydrogen, this is a CH2, CH2, CH3, and this is a hydrogen. So the hydrogen, you remember hydrogen wants to go and hang out with hydrogens. It's just plain rude. But hydrogen will always go to the place where there are more hydrogens. And that's just a rule that you have to remember. So does it matter where you put it? Yes, it matters very much. So the carbon that has more hydrogens directly attached to it will pick up the H, the other carbon will get the hydroxyl. Okay, so just remember those tips and tricks. All right, so now we're going to look at some reactions and do some practical things. So identify the main organic reaction shown as condensation, hydrolysis, oxidation, or reduction. So if I look at this molecule, I'm starting with pyruvate and I go to lactate. So this is something that happens in our bodies and our metabolism. So if I look at them, I'm trying to look and see what changes, right? The CH3 doesn't change. So I'm not really looking at that. This C double bonded to an O, C double bonded to an O with a single oxygen with a negative charge, it's the same. So I'm not really going to look at that. So here I have something that is an aldehyde bonded to 2 carbons. So this is a ketone. And a ketone is going to undergo a reaction and it's going to turn into an alcohol. So do you remember when we didn't have a ketone, we had, if you came up here, an aldehyde, or a ketone, it will still work to go this way. It won't go back the other way, but it will be able to be reduced. So if we look here, we can say what's happening. So here, if I look at everything I haven't crossed out, so I've basically crossed all of this stuff out. So I'm not going to count it anymore. So I'm going to look and see what happened. As I go from pyruvate to lactate, what changed? Well, I didn't change my number of oxygens, but I did add 2 hydrogens. So remember your oil rig. Oxidation is loss of electrons. So I do loss of electrons, gain of oxygen, loss of hydrogen. Here, reduction is gain of electrons, loss of oxygen, gain of hydrogen. So what did I just do? Adding 2 hydrogens, that's a gain of hydrogens. So if I'm gaining hydrogens, I must be reducing. So this is, or a reduction, however you want to say that, REDUC, a reduction reaction. So they wanted you to identify, is it oxidation or is it reduction? When we go from pyruvate to lactate, that's a reduction. If you look at our molecules kind of up here at the top, when we go from NADH to NAD plus, what happened here? Here, as I make this transition, I am actually losing loss of hydrogen. So what is loss of hydrogen? It is oxidation. So these things happen in pairs. Pyruvate's undergoing reduction to form lactate, whereas NADH loses hydrogens in an oxidation reaction to form NAD plus. Okay. All right. Oh, this is a good one. This is a complete combustion. So we're starting with a fatty acid. So a fatty acid, C8H16O2. So this one we're going to undergo combustion, which means we must take our hydrocarbon, that's carbon and hydrogen, so it is a hydrocarbon. We have to add O2 to it, and we have to predict what we're going to make. Well, you know what we're going to make. We know that we're going to make, let's see if I can do this. We're going to make carbon dioxide, that's one thing, CO2, and we're also going to make H2O. So now all I have to do is I have to balance it. And remember, I want to start with things that only occur once. So if I look over here, carbon's only in one place and carbon's only in one place. So that's a fantastic element to start with. Carbon on this side, you assume you have a 1 here. So that's 1 times 8 gives me 8. Over here on the product side, I have carbon. There's a 1 here if there's nothing written. So that would be 1 times, there's a 1 here if there's nothing written. So that's a 1 times 1 gives me 1 carbon. Well, that doesn't match. So I need to multiply my product by a coefficient that would give me 8 atoms of carbon. So if I put an 8 in front here, this is now 8. 8 times 1 gives me 8. So now I have 8 carbons. Well, that's great. Okay. Now my next thing is, do I want to do hydrogens or do I want to do oxygens? Well, I want to do hydrogens because it's only in one compound on either side of the arrow. So that's perfect. So I'm going to pick my hydrogens. And remember, my coefficient is 1 in case you don't notice it, but your coefficient is 1. So I'm going to say 1 times now 16 gives me 16. Come over to my product side, I'll say hydrogens. There's a 1 here if there's nothing written. So 1 times 2, and that's just an underline, it's not negative or anything. 1 times 2 is 2. So that doesn't match. So what times 2 is 16? Well, 8. Okay, so 8 times 2, so I need to put an 8 in front of here, gives me 16. Okay, now I'm going to do my oxygens. It's the only one left. So I have a 1 here. So 1 times 2 gives me 2, but I also have an O2 molecule here. So 1 times 2 gives me 2. 2 plus 2 gives me 4. Okay, let's see what we have on the oxygen side, on the product side. So now we kind of erase all this stuff that I've written. Okay, so now I'm looking at 8 times 2. So let me write that in. 8 times 2 is 16, plus I have 8 times 1 in my water. So 8 times 1 gives me 8. So then 8, 16, 24, that would give me 24 atoms. So that doesn't work out. So what do I need to do in order to get to 24? So I'm going to have to change one of the coefficients if possible. So what could I do? Well, it would be really easy if I could just change my O2 here so that it wouldn't mess up my carbons and my hydrogens. So I'm going to try and focus in on, can I put a coefficient in front of the O2? So can I change this number right here so that my final answer is 24 instead of 4? Well, if that's 24, then this would have to be 22 because 22 plus 2 gives me 24. So how do I get 22? I have to have some number times 2. So that would be 11 times 2 gives me 22. Then 22 plus 2 gives me 24. And then I have the same number on either side. So then I need to make sure to put in my coefficient here of 11. So this is my final balanced chemical equation. Okay. All right. Identify the reactant that's oxidized and the reactant that is reduced in the following reactions. Okay, here we have inorganic molecules. I can see that I have metals and non-metals. And so here I have to track my electrons. So I'm going to write my little oil. Oxidation is loss of electrons, rig, gain of electrons. So reduction is gain of electrons. All right, so what I'm going to do is I'm going to split this reaction into 2 equations. And I'm going to look at what happens to each of the elements in the chemical equation to determine which of the elements is being oxidized and which of the elements is being reduced. So let's start with magnesium. So I'm going to start out with magnesium solid. So that just means all I have is magnesium atoms. There's no ions, so nothing's charged. So it starts out as a 0. That magnesium solid turns into MgCl2. Oh, I don't want to write that there. Let's come over here. I'm going to get MgCl2. So what I need to do is to find out, okay, well, what is the charge on the magnesium? I know there's magnesium, right? I'm pulling out this and I'm pulling out this. And I'm saying, what happens to it? And so I'm going to do that reverse crossover. And I'm going to check my charge on my main group elements. Well, they're both main group elements. And so magnesium is a 2+, so it goes to Mg2+. So then I can say what happens. I go from a charge of 0 to a charge of +2. How did I do that? How did I get more positive? Well, the things that are positive in the atom are the protons. If I change my number of protons, I would change from magnesium to some other element. That's not what happened. What happened was my charge changed, but my proton stayed the same. So the way that that happens is we lose negatively charged particles. We lose negatively charged electrons and become positive. And that's typically what metals do. So if electrons are lost, if we have a loss of electrons, then magnesium is oxidized. So Mg is oxidized, right? So now let's look at what's happening with our other metal. We have iron, Fe. We're starting with FeCl2. All right, so let's do our reverse crossover. So that would mean the 2 would come up and I would get Fe2 plus, then I have a 1, and that would be 1 minus, right? So Cl minus. Check your main group. Chlorine is a -1, and so the iron is a +2. So you start out with a +2 iron, and you go to iron solid. Well, if this is a +2, iron solid is just iron atoms. There's no ions. And so this is a 0. So what do I do when I go from a higher charge to a lower charge? That means I have gained electrons. If you are gaining electrons, that is reduction. So here, iron is reduced. D-U-C-E-D, reduced. Okay. All right, let's try a different color. Okay, I have 2 PbOS. All right, and that is going to 2 Pb plus O2. So if I look at PbO, let's kind of look at that. What's the charge on those? Well, if I do the reverse crossover, right, I get a +1 and I get a -1. But if I go and look on the periodic table, oxygen is not a -1. Oxygen is a -2. And so I'd have to multiply by 2, so I would get Pb plus 2, O minus 2. And so now I can go in and I can see what's going on with these elements, now that I know my charges. So here I have Pb plus 2, and it's going to turn into 2, we don't have to worry about the numbers, PbOS. Okay, so I know that this is a +2. And then I come over here and I see it's a solid. There's no ions, so it's a charge of 0. So what happens when I go from a positive to no charge? That's a gain of electrons, because as I get more electrons, I become less positive. So this one is, Pb is reduced. Okay, how about O? All right, so I'm going to take my oxygen, and it was a charge of -2, so that's a -2 going to O2 gas. Well, O2 is a covalent compound, right? Did I make any ions? No, so I have a charge of 0. So if I go from a negative number to a more positive, in this case, we're only going to 0, but we're still going more positive. So what's happening here is that I am going to lose electrons. As I lose them, I become more positive, and so oxygen is oxidized. And you just got to get familiar in doing that. All right, so now here's some organic reactions, and we're saying that this is either oxidation or reduction. You have to figure out which one is which. So the way that I kind of do this is I kind of look and I go, okay, is this part of the molecule the same? Yes. Okay, I don't have to worry about it. Oh, wait, no, it isn't the same. This is why you do that. Okay, so I'm looking, and you should have seen that this and this are different. As I look at the rest of the molecule, the rest of it looks the same. Okay, so what happens when we could just kind of zoom in on this little portion, right? The rest of it doesn't matter. All you're doing is looking at what's happening when you go from reactant to product. And the only change here is that I have an additional oxygen here. I went from an aldehyde to a carboxylic acid. And so when that happens, I'm undergoing an oxidation reaction, because I know oxidation is a gain of oxygen, and that's exactly what happened. All right, we're looking at B now. B is kind of a whole lot easier to look at, right? Because you're just doing skeletal diagrams. So here this hydroxyl is different, and it's gone there, right? But it's not really gone. The oxygen is no longer there, but there is a hydrogen there. It's just not shown because it's skeletal. So it's not really a loss of hydrogen. The hydrogen is there, but it's bonded to the carbon and not bonded to an oxygen, which is why we don't draw it. So here, when we go from one side to the other, what we're doing is we're losing this oxygen. So now it's gone. So here, this is a loss of oxygen. So this is reduction. Okay. All right. So now we have we're given the starting material. We're told what kind of reaction is going to happen, and then we have to predict the products. So if I look here, reduction. Well, what's going to be reduced? My functional groups are what are going to participate in these kinds of chemical reactions. So basically, I can still draw my ring over here. All right. And that's not going to change. What's going to change is the functional group. So here, I'm still going to keep my carbonyl, but I'm going from a carboxylic acid in a reduction to what? An aldehyde. So if you kind of remember what groups you start with, and if it's a reduction reaction, what do you make? Then you can predict your products really easily, right? And so you could draw the carbon and the hydrogen here, but you don't have to. Technically, because it's skeletal, that's all you have to do. So it's up to you. However, I wouldn't mark it wrong if you did this. That's fine. All right. And that's all we had to do is predict the product. Okay. So let's try another one. Oh, this one we're adding water. So what kind of a reaction happens when we add water, when we go through a hydration reaction, right? So if I look, I'm looking for something that has an oxygen, right? And then we're trying to break this molecule apart. So if I want to break this molecule apart, I'm going to use water in order to break the molecule into two smaller molecules. So what kind of a reaction do we use water to break a big molecule? So that would be hydrolysis. So B is an example of hydrolysis, right? Where we had some kind of ROR, right? And we add water to it. You remember this? HOH. And then this is R1, this is R2. And if I broke it here, then my R1 would pick up the hydroxyl, the OH, and then plus I have an O, I have an R2. So what would be bonded to this oxygen now would be the hydrogen. So this is what we're going to try and replicate with the reagents that we have. So here, I don't have a carbon oxygen carbon. I have a carbon oxygen phosphorus, but I can still do it. So I wouldn't give that to you on a test. I would give you carbon oxygen carbon, but it still works, carbon oxygen phosphorus. So what we're going to do is we're going to break the water and we're going to break our molecule. All right. So which side are we going to break it on? It doesn't really matter. So I'm going to break it right here. All right. So I'm going to have my R1 is here, R1, then this is R2. So if you kind of just break it up that way, it's not so bad to understand, right? And my water, I'm not going to write like that. I'm going to write HOH, and I'm going to break it on either side, doesn't matter. And then let's do this in highlighter, right? So my R1 here does not have the oxygen attached. So it's going to get an oxygen and the hydrogen. So let's write that part out. Let's write just the pink. We have H3. I don't know why I'm in blue. Too many colors. Okay. H3, CH2, C, and then this carbon is going to bond to the oxygen. It's not going to bond to the hydrogen. It's going to bond to the oxygen. And so you'll end with a hydroxyl. So that's one of my substances plus, okay, my next substance, doing blue, right? My next substance is going to be all of this, the oxygen included, right? The oxygen included. So now that is going to pick up, because it already has an oxygen right here, it's just going to pick up the hydrogen. So I'm going to write the hydrogen first. It doesn't matter what you write first. H. Then I'm going to pick up H, and then I'm going to pick up with the oxygen, O. Then I pick up the rest of my R group, P, double bonded to an O, single bonded to an oxygen with a negative, single bonded to an oxygen with a negative. And that is my final product. And you could write that. Sometimes the book will write that as like HPO4 2 minus, but these two things are the same thing. It's just one's the condensed formula and one is the structure, but I would accept either one. Okay, the next one is, we're undergoing oxidation. So you got to remember, what is oxidation? Oxidation is either a gain of oxygen or a loss of hydrogen. So in this case, I'm starting with something that has a carbon and a carbonyl, and it has an R group on this side, and it has a hydrogen. So that must mean that this is an aldehyde. And that aldehyde is going to get converted into a carboxylic acid. And how did I know that? We covered that right here. We said an aldehyde can undergo oxidation and turn into a carboxylic acid. Okay, so we have our aldehyde that goes through oxidation, turns into a carboxylic acid. So my R group doesn't change. So here's my R group. R's don't change. It's only the functional groups. So now I'll turn it into an oxygen, and then I have an OH there. Okay, and that's it. So you just have to kind of like know what you're looking for. All right, now we're going to synthesize aspirin, acetyl salicylic acid. Nice. Through a condensation reaction. So the hydroxyl group from the phenol, so you got to remember, the hydroxyl group from the phenol on salicylic acid condenses with the carboxylic acid group, that's the carboxylic acid group of acetic acid. So this hydroxyl and this hydroxyl are going to participate in the condensation reaction. And so the reason that we have these highlighted, and if you got it in black and white, you might not notice that they're highlighted, but they are highlighted. An oxygen and a hydrogen, those are in red. And so this is actually what's going to come off and going to actually go in and make water, because we know we're going to make HOH. So that HOH is all of the red letters, right? The HOH, these become this. So what's left and how do we connect it? So this oxygen, right? Let's see, this oxygen right here and this carbon right here are the two atoms that are losing bonds. So these two atoms are going to form a new bond with each other. So all we have to do is copy what's there and add the additional stuff to it. So I'm going to start with my ring. And you don't have to be a great artist. I'm not a great artist, but it's kind of fun. Okay, so then see, this one doesn't change, OH, and then it's a double bond to an oxygen. That doesn't change. The only thing that changes, here I have my oxygen, but now instead of having hydrogen, I'm going to follow this little line and make a new bond to the carbon that's in the carbonyl. Give it the carbonyl and give it all of its other stuff. Ooh, CH3. And that's the condensation. So in condensation, I started with two smaller things, and I condensed them into one big molecule, and I made water. But that's the definition of condensation. So you have to know what you're supposed to be doing. All right, fill in the missing organic products from the following hydrogenation reactions. So in a hydrogenation reaction, you are only adding H2. So you are looking for carbons that are participating in a carbon-carbon double bond, and then we're going to add H2, which means we're going to lose one of the bonds. So I'm going to lose one of the bonds, and then each of the carbons is going to pick up one of the hydrogens. So basically it's this carbon and this carbon. They're going to lose a double bond here. This one's going to pick up a hydrogen. This one's going to pick up a hydrogen. So now, what do I have left? Well, here's my carbons. This is my carbon and this is my carbon that were in the carbon-carbon double bond. They're each going to pick up a hydrogen, but do I have to draw it? Nope, because it's a skeletal diagram. So there, done. So easy. All right, now here, we have to predict the reactant, not the product. So what's happening here is that this is our product. Therefore, inside of this ring, if I draw this ring over here, inside of this ring, there had to have been a double bond somewhere, one double bond, because there's no more double bond left. All my lines are crazy. There's no more double bonds that are left. And so now I'm left with the ring. So you can put back a double bond anywhere you want in the ring. Doesn't make a difference. Because when it goes through that addition reaction of hydrogenation, you lose the double bond and each of the carbons picks up a hydrogen, and then it just looks like the ring. So erase that because you wanted the reactant, right? So you got to practice these. Just keep practicing. Okay, that's the last one that I have to practice. But do the ones that you can in the back of the book. They're really, really helpful. All right, good luck.